There's something achingly beautiful about the universe, not just in what we can see, but in what we can't. Picture this, an ocean so vast that no matter how far you sail, entire stretches of it remain forever hidden, locked behind currents too strong to cross. That's our cosmos. For all our telescopes, probes, and equations, there are places out there, entire regions, that might as well be wrapped in shadows, teasing us with their secrets but never letting us in. These are the enigmatic corners of the universe, the ones that defy exploration, no matter how advanced our technology becomes, and that's what makes them so utterly fascinating. Think about it. We've walked on the moon, sent robots to Mars, and even glimpsed the edges of black holes. But beyond those triumphs lie frontiers where the rules seem to twist, where light itself bends into obscurity, and where the very fabric of space and time behaves in ways we can't yet understand. These aren't just empty voids, they're cosmic puzzles, places where the universe seems to whisper, "This far and no further." Scientists call them unexplorable regions, not because we lack curiosity, but because the laws of physics as we know them might never let us reach them. So why do these forbidden zones captivate us so deeply? Maybe it's the human spirit, the part of us that refuses to accept limits, that aches to know what lies beyond the horizon. Or maybe it's the sheer mystery of it all, the way these regions challenge everything we think we know about reality. Whatever the reason, one thing's certain, the universe holds secrets it isn't ready to give up. And today, we're diving into 25 of its most enigmatic realms, places that stretch the boundaries of science, ignite our imagination, and remind us just how much is still out there waiting to be discovered. Buckle up, this journey is about to take us to the edges of the unknown. Black holes aren't just cosmic vacuum cleaners, they're nature's ultimate vaults, locking away mysteries behind a boundary so extreme that even the universe's speed limit, light, can't break free. This point of no return is called the event horizon, and it's where the laws of physics as we know them start to unravel. Imagine standing at the edge of a waterfall where the water doesn't just flow downward but disappears entirely, swallowed by something unseen. That's the eerie stillness of the event horizon, a seemingly calm threshold hiding chaos just beneath its surface. Crossing it would be a grim one-way journey. The gravitational pull near a black hole is so intense that it doesn't just kill you, it redefines death itself. Scientists call the process spaghettification, where the difference in gravity between your head and feet stretches you into a noodle-like strand before tearing you apart atom by atom. But here's the twist. From an outsider's perspective, you'd appear to freeze in time at the event horizon, your image redshifted into oblivion as space-time distorts like a funhouse mirror. You'd be gone, yet somehow eternally suspended, a ghost in the cosmic machinery. What lies beyond? That's where theories spiral into the surreal. Some suggest a singularity, a point of infinite density where space and time cease to exist. Others, like the holographic principle, propose that everything crossing the event horizon gets encoded onto its surface like a celestial hard drive, preserving information in ways we can't yet decode. And then there's the wild card, wormholes. Could black holes be tunnels to other universes or just cosmic dead ends? For now, these questions linger at the edge of science, taunting us with possibilities far stranger than fiction. One thing's certain, the event horizon isn't just a barrier, it's a frontier where our understanding of reality dissolves into shadow. At the heart of every black hole lies a riddle wrapped in a paradox, the singularity. This isn't just a dense object, it's a point where the universe's rulebook gets shredded. Picture this, an entire star's worth of mass crushed into a space smaller than an atom, where gravity becomes so overpowering that space and time lose all meaning. Here, the equations physicists rely on, Einstein's theory of relativity, quantum mechanics, start spitting out nonsense. Infinity isn't just a concept here, it's the only possible answer, and that's a problem. Nature abhors infinity, Reality doesn't do never-ending, so what's really happening at the center, the clash between relativity and quantum mechanics, is where things get messy. Relativity paints the singularity as a smooth, inevitable collapse, while quantum mechanics insists that matter can't just vanish into a dimensionless point. It's like two master painters trying to create the same portrait, one using oils, the other watercolors, and ending up with a canvas that makes no sense. Some theories suggest the singularity might be a knot of exotic matter or a gateway to another universe. Others propose it doesn't exist at all, that quantum effects prevent its formation entirely, leaving behind something even weirder in its place. But here's the cruel twist: we might never know. The singularity is hidden behind the event horizon's impenetrable curtain, and the universe seems determined to keep it that way. Any information about it is locked away, unreachable. Even if we could send a probe, the data would never make it back. It's the ultimate cosmic tease, a mystery we can describe mathematically but never touch, like a shadow that vanishes when you reach for it. And that's what makes the singularity so haunting, not just its violence but its silence. It's the universe's way of saying, some secrets aren't yours to uncover. The so-called dark side of the moon isn't actually dark, it's just shy. This misunderstood hemisphere forever hides from Earth, locked in a cosmic game of peekaboo by tidal forces. As the moon orbits our planet, it rotates at the same rate, keeping one face eternally turned toward us like a dancer spinning perfectly in sync with their partner. The far side basks in sunlight just as often as the near side we see, but its secrets remained out of view until 1959, when the Soviet Luna 3 probe snapped the first grainy photos, revealing a landscape bizarrely different from the familiar craters and seas we know. What makes this hidden realm so geologically alien? Without Earth's gravitational pull distorting its crust, the far side developed a thicker, more rugged shell. Where our side has smooth volcanic plains, the seas early astronomers mistook for water, the far side is a craggy labyrinth of ancient impact basins and towering highlands. The most striking feature, the South Pole Aitken Basin, a colossal scar over 1,500 miles wide and 5 miles deep, holding clues to the moon's violent infancy. Exploring this wilderness is no small feat. Direct communication with Earth is impossible here. Radio signals can't pierce through the moon's bulk. That's why China's Chang'e 4 mission made history in 2019 by landing in the Von Karman crater and deploying the Kuiper relay satellite as a cosmic messenger. The spacecraft's instruments have since detected minerals unlike those on the near side, hinting at a time when the moon's mantle was exposed by apocalyptic collisions. Every pebble studied here rewrites lunar history, but the far side's greatest gift might be silence. Shielded from Earth's radio chatter, it's the perfect spot for telescopes to listen for whispers from the early universe, echoes of the Big Bang itself. This isn't just unexplored territory, it's a time capsule waiting to reveal how planets are born and why ours ended up with life while the moon became a silent guardian of ancient secrets. Far beyond the orbits of Neptune and Pluto, where sunlight dwindles to a faint memory, lies a frozen graveyard of celestial wanderers, the Oort Cloud. This vast spherical shell envelops our solar system like an invisible veil, stretching halfway to the nearest star. Imagine tossing a handful of snowflakes into a stadium. Trillions of icy bodies drift here in the cold dark, each one a pristine relic from the solar system's birth 4.6 billion years ago. These aren't just stray snowballs, they're cosmic time capsules, preserving the original ingredients of planets in deep freeze. Distance alone makes the Oort Cloud unreachable. The nearest edge sits about 2,000 times farther from the Sun than Pluto, roughly a light year away. To put that in perspective, if Earth were a marble in New York, the Oort Cloud would begin somewhere near the coast of Australia. Our fastest spacecraft, like Voyager 1, would need tens of thousands of years just to skim its outer fringe, and here's the kicker, we've never actually seen it. The objects here are too small, too dark, and too spread out, like trying to spot individual fireflies across an entire continent at midnight. Yet this ghostly realm shapes our cosmic destiny. Gravitational nudges from passing stars or galactic tides occasionally send these icy nomads hurtling inward, transforming them into the spectacular comets that streak across our skies. The Great Comet of 1996, Hale-Bopp, that was likely an Oort Cloud visitor, its brilliant tail a fleeting message from the solar system's outermost vault. Some scientists even suspect this icy reservoir could harbor interstellar interlopers, objects like Oumuamua, which may have originated around another star before drifting into our neighborhood. What secrets hide in this frozen frontier? Organic molecules crucial for life might hitch rides on these comets, suggesting the Oort Cloud could have seeded Earth with life's building blocks. Others theorize it could hide rogue planets or even a stealthy companion star to our Sun, though no evidence supports these ideas yet. One thing's certain, until we develop propulsion systems that laugh at the speed of light, the Oort Cloud will remain a kingdom of shadows, a whisper of the solar system's birth, forever teasing us from the cold. The heart of our Milky Way isn't just a place, it's a cosmic riot. Here, 26,000 light-years from Earth, sits Sagittarius, a star, a supermassive black hole with the weight of 4 million suns crushing down into a singularity smaller than Mercury's orbit. Surrounding it is a swirling circus of stars, gas, and radiation so intense it warps the very fabric of space-time. Picture a storm where gravity whips matter around at speeds nearing light itself, where stars don't just orbit but slingshot like crazed comets in a celestial demolition derby. Yet for all this chaos, we're practically blind to the details. Thick veils of cosmic dust block nearly all visible light from reaching us, forcing astronomers to rely on infrared and radio waves to pierce the gloom. It's like trying to spy on a fireworks display through a fogged-up window. You catch glimpses of brilliance, but the full spectacle stays maddeningly out of focus. Even our most advanced telescopes, like the Event Horizon Telescope that captured the first black hole image, strain to decode the frenzied dance around Sagittarius, a star. And then there's the radiation. X-rays and gamma rays bombard the area, lethal enough to fry any probe we might send. The gas clouds here don't just glow, they scream in high-energy frequencies, superheated to millions of degrees as they spiral toward oblivion. Some stars get torn apart entirely, their debris stretched into luminous streamers in a process called tidal disruption. Others, like the star S2, survive absurdly close orbits, enduring gravitational forces that should, by all rights, rip them to shreds. What secrets lie beneath this pandemonium? Theories suggest the black hole's rotation might warp space into a vortex, or that hidden reservoirs of dark matter cluster nearby. Some even speculate about wormholes, hypothetical shortcuts through space-time, though evidence remains as elusive as the calm at the eye of this galactic hurricane. For now, the Milky Way's center remains a monument to nature's extremes, a place where physics is pushed to its limits, and where every new discovery feels like stealing a glance at the universe's best-kept secrets. A neutron star is nature's ultimate pressure cooker, a celestial object so dense that a single teaspoon of its material would weigh 1 billion tons on Earth. These stellar corpses are what remain after a massive star explodes in a supernova, its core collapsing into a sphere no wider than a city, yet packing more mass than our Sun. The surface of such a place isn't just hostile, it's a realm where the very laws of physics twist into surreal extremes. Gravity here is a monster. It's strong enough to flatten mountains, not the towering peaks we know, but microscopic ridges just millimeters high, their atomic structures crushed into submission. Even light struggles to escape, bending so sharply that if you stood on the surface, which you couldn't, because you'd instantly disintegrate, the star's far side would curve into view above you like some warped cosmic carnival mirror. Then there's the magnetism. Some neutron stars, called magnetars, wield magnetic fields a quadrillion times stronger than Earth's. That's enough to rip apart molecules from thousands of miles away, tearing electrons from atoms and reshaping matter into bizarre alien forms. Imagine a force so powerful it could distort the orbits of electrons inside your body, turning you into a cloud of ionized particles before you even knew what hit you. Landing a probe here would be a suicide mission. The star's crust, made of neutron-rich material called nuclear poster, shifts between states as dense as an atomic nucleus and as brittle as dry clay. One wrong move and your spacecraft would be pulverized, either crushed into a smear or vaporized by the star's blistering heat, which can reach 1,000,000 degrees. Even signals sent back to Earth would be garbled by the extreme gravity and magnetic interference, turning crucial data into noise. Yet neutron stars are more than just cosmic death traps. They're laboratories for testing the limits of physics. Their interiors might contain exotic matter, hyperfluid neutrons, free-floating quarks, or even stranger states we haven't discovered yet. Some theories suggest their cores could harbor portals to other dimensions or stable forms of dark matter. Every pulse of radiation from a spinning neutron star, every flicker of its lighthouse-like beams, carries clues about the universe's most extreme environments. So while we may never walk or even safely hover above a neutron star's surface, their mysteries still reach across the void to challenge us. They stand as reminders that the universe doesn't just defy our expectations, it laughs at them, daring us to rethink everything we know about matter, gravity, and the fabric of reality itself. Diving into Jupiter isn't like exploring other planets. It's more like descending into a hurricane that's been raging for billions of years. From space, the gas giant's swirling storms and colorful bands paint a mesmerizing portrait, but beneath those clouds lies a nightmare of physics. The moment a probe crosses the upper atmosphere, it would face winds screaming at over 300 miles per hour, temperatures swinging from -150 degrees to hotter than molten lava, and pressures so intense they'd crumple submarines like soda cans. Current missions like Juno give us glimpses, but only from a safe distance. Orbiting above the cloud tops, Juno maps magnetic fields and peers through Jupiter's veil with microwaves, like trying to study a roaring bonfire by listening to its crackles from another room. Even these cautious observations reveal chaos. Ammonia cyclones wider than Earth, metallic hydrogen rain, and lightning bolts 1,000 times more powerful than anything on our planet. But the real mystery lies deeper, where the rules of chemistry and physics start bending under unimaginable strain. About 600 miles down, hydrogen, the lightest element in the universe, gets squeezed until it morphs into something alien, a liquid metal. This ocean of conductive fluid, churning under pressures 2,000,000 times stronger than Earth's surface, fuels Jupiter's monstrous magnetic field. It's a place where matter exists in a form impossible to recreate in any lab, flowing like water but sparking with electricity like copper wire. Deeper still, temperatures may hit 90,000 degrees hotter than the sun's surface, turning the core into a molten puzzle of rock and exotic ices. Why can't we just send a probe? The answer lies in Jupiter's appetite for destruction. Even if a spacecraft survived the descent, which nothing we've built could, signal transmission would fail long before reaching the core. Radio waves can't punch through hundreds of miles of charged plasma, leaving any last transmissions garbled into static. Galileo's probe in 1995 lasted just 58 minutes before being crushed and vaporized, its sacrifice yielding mere whispers of data from the upper layers. Yet the stakes for understanding these hidden realms couldn't be higher. Gas giants aren't just planetary oddities, they're galactic architects. Their immense gravity shapes solar systems, slinging comets inward or deflecting asteroids away from smaller worlds. Some theories even suggest metallic hydrogen might be a room-temperature superconductor, a material that could revolutionize energy technology if we could somehow harvest it. Until then, Jupiter's interior remains a cathedral of extremes, where the universe reminds us that some frontiers refuse to be conquered, only admired from afar with equal parts awe and frustration. Most maps of the universe are dotted with galaxies woven together by delicate threads of dark matter, except here, the Boötes void isn't just empty space, it's a staggering cosmic anomaly, a spherical desert so vast you could fit 2,000 Milky Ways end to end across it without hitting a single galaxy. Imagine standing in the middle of an empty stadium so large you couldn't see the walls, only to realize the nearest seat, the nearest anything, is miles away. That's the eerie scale of this void, where the usual rules of cosmic structure seem to have been forgotten. Scientists first stumbled upon this ghostly expanse in 1981, expecting to find the usual scattering of galaxies. Instead, they found almost nothing, just 60 or so galaxies where there should have been 10,000. It's like walking into a bustling city only to discover the streets are deserted, the buildings hollow. Theories scramble to explain it. Some suggest smaller voids merged, creating this colossal bubble. Others propose it's the imprint of an ancient cosmic collision, a scar left behind when two regions of space-time tore apart during the universe's infancy. What makes the Boötes void truly unnerving is how it breaks our models. The cosmos isn't supposed to have holes this big. According to standard cosmology, matter should be distributed relatively evenly, like foam in a bubble bath. But this void laughs at uniformity, stretching over 330 million light-years of near-nothingness. Crossing it would be a journey through perpetual twilight, where the nearest source of light might lie tens of millions of years away. A voyage so lonely that by the time you reached the other side, entire species could rise and fall on distant worlds without you ever knowing. Yet even here, mysteries linger. The handful of galaxies that do exist in the void are oddballs, strangely isolated, often smaller and dimmer than their counterparts in crowded galactic neighborhoods. Some glow with unusual intensity, as if burning their fuel in quiet desperation, the only beacons in an endless dark. Could they be refugees from some earlier catastrophe, or did they form under conditions we've never witnessed? The void isn't just empty, it's a hall of mirrors reflecting back questions we're only beginning to ask. For now, the Boötes void remains a humbling reminder that the universe doesn't owe us symmetry. It's a place where the cosmos whispers its most unsettling secret. Sometimes nothingness isn't just absence, it's a statement. Somewhere in the depths of space, beyond the Milky Way's glittering veil, an invisible hand is tugging at the cosmic strings. Hundreds of thousands of galaxies, including our own, are being drawn toward a gravitational enigma so powerful it defies logic, the great attractor. Picture throwing a handful of leaves into a river, only to watch them all drift relentlessly toward a whirlpool you can't see. That's the unsettling effect this region has on everything around it, bending the paths of galaxies like a cosmic puppeteer. The catch, we barely know what it is. The Milky Way's bustling disk of stars, gas, and dust, what astronomers call the zone of avoidance, blocks our view almost completely. It's like trying to study a mountain range through a blizzard. The very stuff that makes our galaxy beautiful also acts as nature's ultimate blindfold. Infrared and radio telescopes have peeled back some of the layers, revealing hints of a colossal cluster of galaxies lurking about 250 million light-years away. But the numbers don't add up. The mass we've detected shouldn't be strong enough to explain the pull we're observing. So what's really out there? One theory suggests the Great Attractor might only be a waypoint, a stepping stone on a much larger cosmic journey. Beyond it lies an even more massive structure, the Shapley supercluster, a sprawling metropolis of galaxies with gravity strong enough to bend light. Some researchers think Shapley's pull might be amplifying the Great Attractor's effect, like a hidden giant guiding a smaller magnet. Others propose darker possibilities, vast concentrations of dark matter, or even exotic physics we haven't yet imagined. Every clue we uncover only deepens the mystery. Galaxies near the Great Attractor move faster than they should, as if caught in an invisible current. The Hubble Space Telescope has captured some of these cosmic travelers, their light stretched and warped by forces we can't directly observe. Meanwhile, projects like the SK Radio Telescope Array aim to map this hidden realm in unprecedented detail, piercing through the galactic fog with beams of radio waves. What's at stake isn't just scientific curiosity, it's a fundamental rewrite of how we understand the universe's structure. If the Great Attractor is merely a shadow of something even larger, our cosmic maps are missing entire continents. The unsettling truth: we're caught in a river of gravity, flowing toward an unknown destination, with no way to see the waterfall ahead. Until we find a way to peer behind the Milky Way's curtain, the Great Attractor will remain one of the universe's most tantalizing riddles, a reminder that sometimes the most powerful forces are the ones we can't see. Venus doesn't just kill spacecraft, it erases them. The planet's surface is a furnace where temperatures hover above 850 degrees Fahrenheit, hot enough to melt lead and fry electronics in seconds. But the heat is only the beginning. A thick, toxic atmosphere 90 times heavier than Earth's presses down with the force of an ocean crushing a submarine at crushing depths. And if that weren't enough, the skies rain sulfuric acid, a corrosive brew that eats through metal and glass like tissue paper. This isn't just an unwelcoming environment, it's a cosmic shredder, dismantling every probe we've dared to send into its grasp. The Soviet Union's Venera program holds the record for surviving this hellscape barely. Between 1961 and 1984, their landers touched down, snapping grainy photos of rust-colored rocks under skies the color of smog. Venera 13, the most resilient, lasted a miraculous 127 minutes before succumbing to the heat and pressure. Its final transmissions revealed a desert of cracked plains under an orange haze, where the very air behaves like a sluggish, superheated fluid. These missions were triumphs of engineering, but also cautionary tales, proof that Venus doesn't tolerate visitors. Modern ambitions like NASA Da Vinci mission aim to outsmart the planet rather than outmuscle it. Instead of relying on brute force landers, Da Vinci will deploy a titanium sphere packed with sensors, designed to sink through the atmosphere like a deep-sea diver descending into an abyss. As it falls, it'll analyze the chemical makeup of those sulfuric acid clouds, hunting for clues about how Venus, Earth's twin in size and origin, became a toxic wasteland. The probe isn't expected to survive impact, but its brief journey could rewrite our understanding of planetary evolution. The stakes are higher than curiosity. Venus might hold warnings about Earth's future. Some scientists suspect it once had oceans, even a habitable climate, before a runaway greenhouse effect turned it into a pressure cooker. Others speculate that its upper clouds, where temperatures and pressures are almost Earth-like, could harbor extremophile microbes, floating like microscopic survivors in a poisoned sky. But verifying any of this requires piercing the planet's defenses, a challenge that pushes robotics to their absolute limits. For now, Venus remains the solar system's forbidden fortress, a world that mocks our exploration efforts with violent indifference. Every failed lander, every melted circuit is a reminder: some frontiers don't surrender easily. They force us to innovate, to rethink, and sometimes to accept that the universe keeps its secrets locked tight, at least for now. If the universe has a dragon, it's a magnetar, an ultra-dense neutron star armed with a magnetic field so monstrous it defies comprehension. We're not talking about refrigerator magnets here. These cosmic beasts wield forces a quadrillion times stronger than Earth's, capable of shredding atoms into subatomic confetti from halfway across a solar system. Picture this: a magnetic grip so intense it could rip the iron from your blood from 50,000 miles away before your nerves even registered the danger. That's the raw, terrifying power of a magnetar. What makes them so different from ordinary neutron stars? It's all in the spin. When certain massive stars collapse, their cores don't just compress, they twist, winding magnetic fields into knots tighter than a black hole's grip. The result, a dynamo of destruction, where magnetic energy builds until it cracks the star's crust like an eggshell, unleashing starquakes that ripple across space-time. These quakes trigger magnetar flares, sudden, violent outbursts of gamma rays and X-rays brighter than 1,000,000 suns. One such flare, detected in 2004, actually compressed Earth's upper atmosphere from halfway across the Milky Way, briefly disabling satellites and lighting up our sky like an artificial aurora. Observing these monsters up close isn't just difficult, it's suicidal. Any spacecraft venturing within a few 100,000 miles would be atomized. First, its circuitry would fry from the relentless X-ray bombardment. Then, the magnetic field would twist its metal hull into a pretzel, snapping molecular bonds like dry twigs. Even at a safe distance, the radiation would garble transmissions into static, leaving scientists blind. That's why we study them from the cosmic back row, relying on telescopes like Chandra and Fermi to catch glimpses between flares. Yet magnetars aren't just destroyers, they're also cosmic Rosetta Stones. Their extreme physics could unlock secrets about quantum mechanics, dark matter, and even the birth cries of black holes. Some theories suggest their magnetic fields might momentarily open portals to higher dimensions, or that their interiors harbor strange matter never seen on Earth. Every flicker of gamma rays carries encrypted clues if only we could decode them. So while we may never send a probe into a magnetar's killing zone, their very existence stretches our understanding of reality. They're reminders that the universe doesn't just play by rules, it writes them in lightning, then dares us to read between the lines. The universe doesn't just expand, it accelerates, fleeing from itself in a runaway dance that grows faster with every passing eon. Billions of years from now, this acceleration will rewrite the cosmic story in letters of fading light, leading to one of two possible finales, the heat death or the big rip. Both scenarios are less like endings and more like slow-motion erasures of reality itself, where the very fabric of existence unravels in ways that defy human intuition. Heat death is the universe's quietest apocalypse, a whisper, not a bang. As galaxies race apart, their stars burn out one by one, leaving behind skeletons of black holes and cold, dead planets. With no new matter forming, nuclear furnaces flicker off and entropy maxes out. Space becomes a featureless graveyard where temperatures hover just above absolute zero, and particles are so spread out they might as well be alone in the void. Time loses meaning because nothing changes anymore. No energy flows, no life stirs. It's the ultimate equilibrium, a cosmic flatline, but the big rip. That's nature's tantrum. If dark energy, the mysterious force driving the universe's expansion, grows stronger over time, it won't just push galaxies apart. It'll tear them apart. First, galaxy clusters would be ripped into isolated islands. Then, stars would be plucked from their galaxies like grapes from a stem. Planets would detach from their suns. Eventually, even atoms couldn't hold themselves together. Protons and electrons would be wrenched apart, and space-time itself would shatter into fragments. The universe wouldn't just end, it'd be dissected. Here's the cruel twist: we'll never witness either outcome. These events unfold on timescales so vast they dwarf human existence. The universe is roughly 13.8 billion years old, but heat death wouldn't begin for another 10 to the power of 100 years. A number so large it has more zeros than atoms in the observable universe. By then, humanity, if it even still exists, won't resemble anything we'd recognize. Our tools, our science, even our concept of observation would be meaningless in a cosmos where information itself is irretrievably scattered. That makes these theories both profound and untestable. They're extrapolations based on today's physics, projected onto a canvas so enormous we can't even call it speculative. It's like trying to predict the fate of a single raindrop in a hurricane by studying a single molecule of water. Yet contemplating these endings forces us to confront the universe's most humbling truth. Everything, stars, planets, even the laws of physics, might be temporary. The cosmos doesn't owe us permanence, it doesn't owe us answers, it simply expands, indifferent to the tiny flickers of consciousness trying to decode its fate. For now, these distant dooms remain thought experiments, shadows cast by the flickering light of our current understanding. But they remind us that the universe's story doesn't end with us or with anything we'd recognize. It's a narrative written in chapters too long for any reader to finish, too vast for any mind to fully grasp, and perhaps that's the most haunting mystery of all, not how the universe ends, but how little of its story we're here to witness. At the smallest scales imaginable, far beyond the reach of even the most powerful microscopes, space-time itself might not be the smooth, unbroken fabric we imagine. Instead, it could be a seething, turbulent ocean, a froth of quantum foam where reality flickers in and out of existence. This isn't just empty space, it's a realm where the very concepts of here and now lose meaning, where subatomic particles blink into being only to vanish moments later, like bubbles in a boiling pot. Welcome to the Planck scale, where the universe's rulebook gets tossed out the window, and the laws of physics as we know them dissolve into chaos. The idea of quantum foam comes from the clash between two titans of physics, Einstein's theory of general relativity, which governs the cosmos on large scales, and quantum mechanics, which dictates the behavior of the impossibly small. General relativity describes spacetime as a smooth, flexible sheet warped by gravity. Quantum mechanics, on the other hand, thrives on uncertainty, where particles pop in and out of existence at random. But when you try to mash these two theories together at the Planck scale, about 10 to the power of minus 35 meters, or a billionth of a trillionth the size of a proton, spacetime itself starts behaving erratically. It's like trying to paint a masterpiece on a canvas that's constantly tearing and stitching itself back together. What would this foam look like if we could see it? Picture a stormy sea, but instead of waves, there are countless microscopic black holes and wormholes forming and vanishing in an instant. Time and space might twist into knots, creating tunnels that lead nowhere or everywhere before collapsing under their own absurdity. Some theories suggest these fleeting wormholes could even link distant parts of the universe, making spacetime a labyrinth of shortcuts that exist only for a fraction of a second. Others argue that the foam is a byproduct of virtual particles, ghostly counterparts to real matter that borrow energy from the vacuum of space, only to repay it before nature notices the debt. Here's the ultimate frustration. We'll likely never observe quantum foam directly. The Planck scale is so mind-bendingly tiny that probing it would require energies a quadrillion times greater than what our most powerful particle colliders can produce. Even if we could concentrate that much energy into a single experiment, the resulting collision might create a black hole, swallowing the evidence before we could study it. It's like trying to study the ripples in a pond by dropping an ocean onto it, destructive and utterly futile. Yet the implications ripple outward. If spacetime truly is foamy at its foundation, it could explain why gravity refuses to play nice with quantum theory. It might hint at hidden dimensions or reveal why the universe seems fine-tuned for life. Some physicists even speculate that the foam's turbulence could leave faint fingerprints on light traveling across the cosmos, subtly distorting the paths of gamma rays over billions of years. These distortions, if detected, would be our first indirect glimpse into this frenzied underworld of reality. For now, quantum foam remains a tantalizing mirage, a mathematical prediction hovering just beyond the edge of empirical proof. It's a reminder that the universe's deepest secrets aren't just hidden in distant galaxies or ancient light. They're woven into the very fabric of existence, dancing in the spaces between our measurements, teasing us with possibilities we can't yet grasp. And that's the beauty of it. Some mysteries don't just challenge our science, they challenge our imagination. At the heart of certain galaxies, a cosmic monster is feeding, and it's loud enough to be heard across the universe. These are quasars, the brightest objects in existence, powered by supermassive black holes devouring matter at a gluttonous pace. But calling them bright doesn't do them justice. A single quasar can outshine an entire galaxy of hundreds of billions of stars, its brilliance visible from billions of light years away. That light isn't just starlight, though. It's the death scream of matter spiraling into oblivion, heating up to millions of degrees before vanishing behind the event horizon. What makes quasars so alien isn't just their appetite, but their architecture. Imagine a black hole spinning at nearly the speed of light, wrapped in a glowing disk of superheated gas, a cosmic hurricane where magnetic fields twist into coils tight enough to launch jets of plasma at nearly light speed. These jets, stretching hundreds of thousands of light years into space, act like interstellar blowtorches, carving through galaxies and lighting up intergalactic gas like neon signs in a fog. The energy here is incomprehensible. A single quasar's output could power human civilization for trillions of years if we could somehow tap into it. Yet for all their fury, quasars are cosmic will-o'-the-wisps. Their brilliance comes from their accretion disks, the swirling maelstroms of gas and dust just outside the event horizon, but the black hole itself, that's invisible, shrouded behind the very disk that announces its presence. We're left studying the shadows and echoes of these monsters, interpreting their light like astronomers deciphering a distant bonfire through thick smoke. Even if we could travel to one, the environment is so hostile it defies survival. The radiation near a quasar's core would fry any known material instantly, turning spacecraft and instruments into vapor before they could send back data. Distance compounds the problem. Most quasars lie billions of light years away, meaning we're seeing them as they were when the universe was young, ancient relics flickering from the depths of time. Their light takes so long to reach us that by now, many have likely devoured all nearby fuel and gone dark, leaving behind dormant black holes. We're essentially studying ghosts, their brilliance a snapshot of a frenzy that ended before Earth even formed. That hasn't stopped astronomers from trying to peel back the layers. By analyzing the flickers in a quasar's light, they've mapped the turbulent structures of accretion disks. Some theories suggest magnetic fields in these disks might act like cosmic particle accelerators, whipping matter to energies far beyond anything we could recreate on Earth. Others speculate that quasars could be portals. Their jets might inject energy into the cosmic web, the vast network of gas filaments connecting galaxies across the universe. But the core remains a locked vault. No probe will ever plunge into a quasar's heart. No camera will ever glimpse the chaos just outside the event horizon. These are places where physics stretches to its breaking point, where gravity and radiation dance in a lethal embrace. Quasars teach us a humbling lesson. Some of the universe's most spectacular phenomena aren't just unexplorable. They're unfathomable beacons from the edge of reality, burning too bright to ever see clearly. Proxima b dangles the tantalizing possibility of another Earth, a rocky world nestled snugly in the habitable zone of our closest stellar neighbor, Proxima Centauri, a mere 4 light-years away. But this potential paradise comes with caveats that make it less a welcoming shore and more a mirage shimmering just beyond our reach. Even with today's most advanced telescopes, peering at its surface is like trying to read a book through a fogged-up window while standing in a hurricane. The first hurdle is Proxima Centauri itself, a red dwarf star with a temperamental streak. Unlike our steady sun, this star unleashes violent flares, some hundreds of times more powerful than anything in our solar system. These eruptions bathe Proxima b in radiation, potentially stripping away any atmosphere and bombarding the surface with enough X-rays to sterilize it. Imagine a world where the sky periodically erupts in lethal firestorms, where the very air might be ripped away by stellar tantrums. That's the daily reality for any life or robotic explorer that might try to call this place home. Then there's the communication nightmare. 4 light years might sound like a short hop on the cosmic scale, but it's an abyss for real-time exploration. A signal from Earth takes 4 years to reach Proxima b and another 4 for a response to come back. That means a simple hello would take nearly a decade to complete a round trip. Controlling a rover, forget it. Every command would need to be pre-programmed with zero room for error or adjustment. It's like playing chess where you only get to move a piece once every 8 years blindfolded. Current technology only magnifies the frustration. Our best space telescopes like James Webb can analyze Proxima b's atmosphere, if it has one, by studying the faint shadows it casts during transits. But capturing surface details, that's like trying to photograph a firefly hovering next to a spotlight from 1,000 miles away. Even envisioned missions like Breakthrough Starshot, which aims to send gram-scale probes propelled by lasers, would face staggering challenges. These tiny craft, traveling at 1/5 the speed of light, would still take 20 years to arrive, and that's assuming they survive the journey through interstellar dust and radiation. Yet the allure persists. Proxima b represents something primal, the dream of stepping onto another world that isn't just a frozen rock or a toxic hellscape. Its existence forces us to ask uncomfortable questions. Can life thrive under such extreme conditions? Or is this planet a cautionary tale, showing us that habitable zones around red dwarfs might be cosmic traps? Until we develop faster propulsion, better shielding, or revolutionary new observation techniques, Proxima b will remain a riddle, a neighbor so close yet forever out of reach. And perhaps that's the most frustrating truth of all. In the vast ocean of space, the nearest island might be the one we can never visit. Beyond Pluto's frozen plains lies a graveyard of cosmic leftovers, the Kuiper Belt, a sprawling donut of icy rubble stretching billions of miles into the void. This isn't just some distant junkyard, it's a time capsule from the solar system's violent birth, where objects like Arakoth, a primordial snowman-shaped relic, float unchanged for 4.5 billion years. But the farther you travel into this frigid wilderness, the stranger things get. Out here, where sunlight is 1,000 times dimmer than on Earth, the Kuiper Belt's outer edges dissolve into a twilight zone of half-formed worlds and hypothetical giants, a place so remote it defies exploration even as it rewrites our cosmic origin story. Arakoth, the most distant object ever visited by a spacecraft, offers a glimpse into this frozen archive. When New Horizons zipped past it in 2019, it revealed a bizarre double-lobed structure resembling 2 pancakes glued together. A fossil from the era when dust grains gently collided and stuck, building the solar system piece by piece. No violent crashes, no searing heat, just slow, chilly dances in the dark. This is how planets might have begun, not in fire but in frost. Yet for every Arakoth we've spotted, thousands more lurk unseen, cloaked by distance and the feeble glow of a sun reduced to little more than a particularly bright star. The real enigma starts where the known Kuiper Belt ends. Around 50 astronomical units out 50 times farther than Earth is from the Sun, the orderly scattering of objects begins to fray. Orbits skew wild, clustering in ways that shouldn't happen by chance. This anomaly has scientists whispering about Planet 9, a hypothetical world up to 10 times Earth's mass lurking somewhere in the icy dark. Its gravitational pull, they theorize, could be herding these distant bodies into strange formations, but finding it, that's like searching for a black cat in a coal cellar, armed with nothing but a flickering candle. Current telescopes can barely scratch the surface of this frontier. The Vera C. Rubin Observatory, set to scan the skies in the next few years, might spot Planet 9 if it exists. But even then, confirming its nature would require missions we can't yet build. The outer Kuiper Belt is so cold that typical spacecraft electronics would freeze solid, and signals from probes would take days to crawl back to Earth at light speed. Worse, the dimness of these objects means they're often discovered only by accident, their faint reflections caught in the corner of a telescope's eye. What's out there isn't just a mystery, it's a mirror. The Kuiper belt's outer fringes could hold the recipe for our solar system's formation, or evidence of long-lost sibling planets ejected into the dark. Some models even suggest its icy bodies might be interstellar trespassers, captured from other stars in the Milky Way's crowded infancy. Until we develop telescopes sensitive enough to map this frozen fringe or brave enough probes to plunge into its depths, the Kuiper belt's outermost secrets will remain just that, whispers from the cold, hinting at truths we're not yet equipped to hear. If black holes are the universe's one-way doors, white holes are the emergency exits, at least in theory. These hypothetical cosmic twins flip the script on everything we know about singularities. Instead of pulling matter in past a point of no return, a white hole would violently spit it out, refusing to let anything cross its threshold from the outside. Picture a reverse black hole, a cosmic fountain gushing energy and matter into spacetime with such force that nothing could ever push its way back in. But here's the catch: white holes might not exist at all. They're mathematical phantoms, solutions to Einstein's equations that physicists debate could be real or just fascinating thought experiments. The idea emerges from the same equations that predicted black holes. If you take general relativity and run the clock backward on a black hole's collapse, voila, you get a white hole. Some theories suggest they could be the other end of an Einstein-Rosen bridge, better known as a wormhole, with matter falling into a black hole somewhere only to erupt from a white hole elsewhere. Others propose they're remnants of black holes that somehow stopped evaporating via Hawking radiation, rebounding into existence like a deflated balloon suddenly reinflating. The wildest speculation that the Big Bang itself was a white hole event, the ultimate cosmic expulsion. But even if white holes are real, reaching one would be impossible. Unlike black holes, which form from dying stars, white holes, if they exist at all, would likely be relics of the early universe. The expansion of spacetime would have flung them to inconceivable distances by now, pushing them beyond our observational horizon. Light from these objects, if any escaped, would be redshifted into oblivion, lost in the background hum of the cosmos. And here's the cruel irony. While a black hole's event horizon traps everything inside, a white hole's event horizon repels everything outside. Approach one, and you'd be hit with a wall of radiation and particles moving at near light speed, like trying to swim upstream in a tsunami. What makes white holes so tantalizing isn't just their defiance of intuition, it's what they imply about our universe. If they're real, they'd challenge our understanding of entropy, causality, and even time's arrow. A black hole's singularity represents a future where physics breaks down. A white hole's would be a past singularity, a moment where the universe's rules reset. Some models suggest they could be hiding in plain sight, masquerading as gamma-ray bursts or even dark matter sources. But without evidence, they remain ghosts in the equations, reminders that the universe's strangest possibilities might always stay just out of reach. So for now, white holes linger at the edge of physics, beautiful, untouchable, and perhaps entirely imaginary. They're cosmic mirages, teasing us with the idea that somewhere, somehow, the universe might have a backdoor. Until we find a way to peer beyond the math, they'll remain one of cosmology's greatest what-ifs, a shadow cast by the light of black holes, forever retreating into the unknown. The Milky Way doesn't just spin through space, it's wrapped in an invisible cocoon, a vast halo of dark matter 10 times more massive than all its stars, gas, and dust combined. This ghostly scaffold stretches hundreds of thousands of light-years beyond the galaxy's glittering disk, its gravity silently shaping the orbits of stars and bending the paths of light itself. Yet despite making up 85% of the universe's matter, dark matter refuses to play by the rules we know. It doesn't shine, absorb, or reflect light. It doesn't collide with atoms or stack into planets. It's the universe's most influential introvert, weaving the cosmic web while leaving barely a trace of its presence. So how do we know it's there? The clues are written in the stars, literally. In the 1970s, astronomer Vera Rubin noticed something bizarre. Stars at the edges of spiral galaxies were moving just as fast as those near the center. According to Newton's laws, they should have been slowing down like outer horses on a carousel, lagging behind the inner ones. The only explanation, an enormous amount of invisible mass, its gravitational pull whipping those stars to unexpected speeds. Later, observations of gravitational lensing where distant galaxies appear warped by unseen mass confirmed it. Dark matter wasn't just a Milky Way quirk. It was the universe's hidden architecture, holding galaxies together like invisible glue. But if it's everywhere, why can't we touch it? The problem lies in its aloofness. Unlike ordinary matter, dark matter seems to interact only through gravity, ignoring the electromagnetic force that makes atoms stick together. It's like trying to catch smoke with your bare hands. You can see its effects, but your fingers close on empty air. Scientists have spent decades building detectors deep underground, shielding them from cosmic noise in hopes of catching a rare collision between dark matter particles and ordinary atoms. So far, silence. Even the Large Hadron Collider, which smashes protons at near-light speeds, hasn't found a shred of evidence. Theories abound. Some suggest dark matter is made of WIMP, weakly interacting massive particles that pass through Earth like ghosts. Others propose actions, ultra-light particles that could transform in magnetic fields. There are even wilder ideas that dark matter is primordial black holes from the universe's first second, or particles from hidden dimensions we can't perceive. But the longer experiments come up empty, the more physicists wonder if they're missing something fundamental. Could gravity itself behave differently at galactic scales? Or is dark matter an illusion, a cosmic mirage created by gaps in our understanding? The Milky Way's halo is the perfect laboratory for these questions. Its sheer size means even feeble interactions could add up to detectable signals. Astronomers scour its edges for gamma rays that might hint at dark matter particles annihilating each other. Others study hypervelocity stars, flung from the galaxy's core by the halo's gravitational tides, as living tracers of its shape. And then there's the Gaia spacecraft, mapping 1 billion stars with precision, revealing how their dances are choreographed by the halo's unseen hand. Yet the more we learn, the stranger dark matter seems. Recent simulations suggest the Milky Way's halo might be lumpy, clumped into invisible islands that ripple through the galaxy's outskirts. Some models even hint that dark matter could form its own shadow galaxy structures mirroring our visible ones but utterly unreachable, the cruelest irony. This stuff surrounds us, passes through us every second, and we're no closer to knowing what it is. It's as if the universe built a stage, then hid the scaffolding and dared us to figure out how it stands. Until we crack that code, the Milky Way and every galaxy will keep spinning in the dark, anchored by a mystery we can't see, touch, or explain. Rogue planets are the cosmic nomads, worlds that wander the interstellar darkness without a sun to call home. Unlike Earth, anchored in the warm glow of our star, these lone drifters exist in perpetual twilight, untethered from any solar system, cruising silently through the void. Some were flung from their birthplaces by violent gravitational encounters. Others may have formed alone in the cold cradles of gas clouds too sparse to ignite into stars. The result, a planet where the sky is forever black, where the concept of day doesn't exist, and where the only warmth comes from the faint simmering of radioactive decay deep in its core. Imagine standing on the surface of one. The ground beneath you might be frozen nitrogen or methane, as hard as steel, cracking under temperatures hundreds of degrees below zero. Above, no sunrise paints the horizon, just an endless expanse of stars, unmoving, unchanging, like a static painting. The silence would be absolute. no wind, no weather, just the faint vibration of the planet's slow tectonic groans. And yet, even here, there could be surprises. Some rogue planets might harbor underground oceans kept liquid by tidal forces or geothermal heat, hidden beneath miles of ice. These buried seas could, in theory, host life extremophiles clinging to hydrothermal vents, cut off from the universe above, never knowing the concept of a sun. The challenge of finding these vagabond worlds is immense. Without a star's light to reflect, they're virtually invisible. Astronomers must rely on microlensing, a fleeting distortion of starlight as the planet's gravity bends it like a lens, or the faint infrared glow of its cooling surface. Even then, detecting one is like spotting a candle lost in a fog bank, and landing, forget about it. A spacecraft sent to such a planet would face a descent with no guiding light, no atmospheric entry profile to predict, and no hope of solar power to keep it running. Batteries would freeze, instruments would shatter, communication would be near impossible over interstellar distances, with signals taking years to reach home. Yet rogue planets might be far more common than we think. Some estimates suggest there could be billions drifting unseen through our galaxy alone, outnumbering stars by a wide margin. Their existence forces us to rethink what makes a planet habitable. If life can cling to deep-sea vents on Earth, why not in the abyssal oceans of a rogue world where geothermal vents might persist for billions of years? Some theories even suggest these planets could act as interstellar arcs, carrying microbial life between stars, seeding the galaxy in slow, patient hops. For now, though, they remain shadows, elusive, untouchable, haunting the spaces between the stars. Every new detection is a triumph of technology and deduction, a brief glimpse into the lives of worlds that play by no one's rules. They remind us that the universe is stranger and more diverse than our solar system could ever suggest, full of dark, lonely travelers on journeys we may never fully trace. And in that darkness, there might just be secrets waiting, whispers of life, of formation, of cosmic history frozen in the void, waiting for us to listen. The Planck epoch is where physics itself dissolves into uncertainty, a sliver of time so brief it makes a nanosecond feel like an eternity. We're talking about the first 10 to the power of -43 seconds after the Big Bang, a moment when the universe wasn't just young, it was embryonic. Temperatures soared to 10 to the power of 32 degrees, energy so extreme that the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were fused into a single, indecipherable superforce. This wasn't merely a hotter, denser version of today's cosmos. It was a realm where the very concepts of space and time flickered in and out of existence, a quantum foam of reality itself. Why can't we recreate these conditions? The numbers alone are staggering. To probe the Planck epoch, we'd need a particle collider the size of a galaxy, capable of energies 1 trillion times beyond what the Large Hadron Collider can muster. Even if we could build it, the collision would likely birth a black hole, swallowing the experiment whole. It's like trying to study the roots of a tree by detonating a bomb beneath it. The very act of observation would destroy the thing we're trying to understand. Inflation theory offers a tantalizing workaround. Some models suggest the universe underwent exponential expansion in its first slivers of existence, stretching a speck smaller than a proton to the size of a grapefruit in less than a blink. This would explain the cosmos' eerie uniformity, the way the night sky looks roughly the same in every direction. But here's the catch: inflation's energy scales are tied to the Planck epoch. Without direct evidence, it's like reconstructing a crime scene from a single, blurry fingerprint. The cosmic microwave background, that afterglow of the Big Bang, gives us hints, but it's a snapshot taken 380,000 years after the Planck epoch, an eternity in cosmic terms. The deeper irony: quantum mechanics and general relativity, our two most successful theories, become mutually incomprehensible here. relativity paints space-time as a smooth continuum, while quantum mechanics demands everything be granular. In the Planck epoch, these frameworks clash violently, like two actors trying to perform different plays on the same stage. String theory and loop quantum gravity attempt to bridge the gap, but without experimental data, they're like maps drawn from rumors. So we're left with a cosmic chicken and egg problem. To understand the universe's birth, we need a theory of quantum gravity. But to test that theory, we'd need access to energies only present at the universe's birth. It's the ultimate closed loop, a puzzle locked inside a vault we can't crack. For now, the Planck epoch remains a shadow theater, a performance we can describe mathematically but never witness, playing out in a time before time had meaning. And perhaps that's the most humbling truth of all. Some frontiers aren't just distant, they're fundamentally, beautifully unreachable. Brown dwarfs are cosmic misfits, too massive to be planets, yet too puny to ignite the nuclear fires that define a true star. Stuck in this awkward in-between, they glow faintly with the leftover heat of their birth, like embers cooling in the ashes of a dying fire. But don't let their dim glow fool you. Peering inside one of these failed stars is like trying to decode a sealed letter written in vanishing ink. Their turbulent atmospheres, choked with exotic metals and swirling storms, cloak interiors so extreme they defy even our most advanced simulations. Take a journey into the depths of a typical brown dwarf, and you'd encounter layers stranger than science fiction. The outer atmosphere is a riot of methane and ammonia clouds, whipped into frenzy by winds faster than jet streams. Beneath that, pressures mount until hydrogen, normally a gas, behaves like a liquid metal conducting electricity in a churning sea. Deeper still, temperatures soar to tens of thousands of degrees, but without the stabilizing force of fusion, the core is a slow-motion collapse, a perpetual almost star straining against its own weight. The cruel irony, we'll likely never send a probe into this abyss. Brown dwarfs lack the dramatic flares of stars or the solid surfaces of planets, making them invisible to most traditional exploration methods. Their faint infrared glow is often drowned out by brighter cosmic neighbors, and their thick atmospheres absorb or scatter any signals we might try to send. Even if we could penetrate the haze, the pressures inside would crush any instrument long before it reached the core. That leaves scientists relying on indirect clues, subtle flickers in their light, the way their gravity tugs on nearby objects, to piece together theories about what lurks beneath. Some models suggest their cores might harbor exotic states of matter, like degenerate electron soup or even crystalline phases of hydrogen. Others speculate that the deepest layers could act as natural particle accelerators, sparking rare nuclear reactions without full-blown fusion. Then there's the wild card. Could brown dwarfs host magnetic fields so intense they rival neutron stars? A few observed examples emit radio bursts eerily similar to pulsars, hinting at dynamos of unimaginable power churning in their depths. Yet for all their mystery, brown dwarfs might be the universe's hidden majority. Some estimates suggest they outnumber stars in our galaxy, lurking in the dark like cosmic phantoms. Their very existence blurs the line between planet and star, forcing us to question how celestial bodies are born, evolve, and fade. And perhaps that's their greatest lesson. Sometimes the most fascinating things in the universe aren't the brightest or the most violent, but the ones that linger in the shadows, whispering secrets we're not yet equipped to hear. The Milky Way doesn't just light up our night sky, it blinds us. There's a vast stretch of the cosmos directly behind our galaxy's core, where stars, gas, and dust pile up so thickly they form an impenetrable curtain. Astronomers call it the zone of avoidance, and it's not just a minor inconvenience. It's a colossal blind spot hiding millions of galaxies that should theoretically be there. Imagine trying to study a bustling city skyline, but someone's parked a skyscraper right in front of your window, blocking the view. That's the frustration astronomers face when they peer toward this forbidden zone. The Milky Way's disk is crammed with cosmic clutter. Dust grains as fine as smoke particles absorb visible light, while dense star fields drown out distant galaxies in a glittering haze. Even infrared telescopes struggle here, their vision muddled by the heat glow of interstellar material. The result, a swath of sky covering about 20% of the visible universe, where traditional astronomy hits a wall. We know the galaxies must exist. Large-scale structure models predict them, but they're effectively ghosts, their presence inferred only by the gravitational tugs they exert on surrounding visible matter. Radio waves, however, slip through where light cannot. Projects like the Square Kilometre Array, or SCAR, aim to pierce this veil with antennas tuned to frequencies that ignore dust and stars. By mapping hydrogen emissions, the faint radio whispers of distant galaxies SKA could reveal the hidden architecture of the zone of avoidance, uncovering galactic superclusters currently lost in the noise. Early surveys with smaller arrays have already teased tantalizing hints: odd distortions in cosmic background radiation, peculiar velocities of nearby galaxies suggesting unseen masses pulling at them. It's like hearing the echoes of a conversation through a closed door, knowing there's a party inside but unable to see the guests. Yet even radio has its limits. The sheer density of foreground noise from the Milky Way's own radio-bright objects, pulsars, supernova remnants, and star-forming regions creates a cacophony that algorithms must painstakingly untangle. And then there's the problem of resolution. The farther behind the galactic plane a galaxy lurks, the fainter its signal becomes, stretched thin by the very dust that obscures it. Peering into the zone of avoidance isn't just a technical challenge. It's an exercise in cosmic forensics, reconstructing a crime scene where the evidence has been scattered and buried. What might we find if we succeed? The most exciting possibility is the great attractor's missing piece. This mysterious gravitational anomaly, pulling our local galaxy cluster toward it, lies partially obscured by the zone. Some theorize that a colossal cluster of galaxies, nicknamed the Massive Great Wall, could be lurking there, its gravity amplifying the pull we detect. Others speculate about dark matter structures so vast they warp the fabric of local space-time. Whatever's hiding there, it's rewriting our maps of the cosmos, forcing us to admit just how much we've been missing. For now, the zone of avoidance stands as both a barrier and a beacon, a reminder that the universe often hides its grandest designs just out of sight. But with every radio pulse decoded, every gravitational clue unraveled, we're inching closer to lifting the Milky Way's veil. And when we do, the hidden galaxies we uncover won't just fill in blank spots on our atlases. They'll redefine our place in the cosmic web, revealing just how much of the story we've been missing. Beneath Europa's frozen, scarred surface lies one of the solar system's most tantalizing secrets, a global ocean of liquid water, hidden under miles of ice but kept warm by the relentless gravitational squeezing of Jupiter. This isn't some shallow, briny puddle. It's a body of water with twice the volume of all Earth's oceans combined, encased in a shell so thick and ancient it might as well be a vault. And if there's one place beyond our planet where life could cling to existence, this is it. The ingredients are all here: liquid water, organic molecules, and hydrothermal vents churning out energy like underwater geysers. But Europa guards its secrets fiercely, wrapping them in layers of ice that challenge even our boldest engineering dreams. Getting to that ocean is like trying to break into a high-security bunker buried under an Arctic glacier. The ice crust averages 10 to 15 miles thick, deep enough to bury Mount Everest twice over. And this isn't your backyard pond ice. It's a dynamic, fractured labyrinth, riddled with crevices and shifting plates, where temperatures hover around -200 degrees Fahrenheit at the surface. Even if we could land a drill here, conventional methods would fail spectacularly. A mechanical drill bit would seize up like a car engine in a blizzard, its mechanisms frozen solid before reaching even a fraction of the needed depth. Then there's the radiation. Europa orbits deep inside Jupiter's lethal magnetic field, a zone where charged particles whip around at near light speed, creating a death zone for electronics. The Moon's surface is bombarded with 5.4 sieverts of radiation per day, enough to kill an unshielded human in hours and fry spacecraft circuits in weeks. Any drilling operation would need to be fully autonomous, its brain shielded by layers of lead or water, communicating through brief, heavily encrypted bursts to Earth. It's like performing brain surgery with oven mitts while someone fires a microwave at your hands. Yet the reward might justify the risk. Europa's ocean doesn't just mirror Earth's deep-sea ecosystems, it could surpass them. Hydrothermal vents on our ocean floor support entire communities of extremophiles, creatures thriving in boiling, mineral-rich plumes without a lick of sunlight. Europa's seafloor, heated by tidal friction and radioactive decay, might host similar oases or something far stranger. Some models suggest its water could be rich in oxidants, chemicals brewed on the surface by radiation and then transported downward through cracks in the ice, creating a slow but steady nutrient cycle. Life here wouldn't need the sun. It'd need only chemistry, time, and a little luck. NASA's upcoming Europa Clipper mission aims to scout the territory, mapping the ice shell and hunting for plumes that might spew ocean water into space. But touching that ocean, that'll take a technological leap we haven't yet made. Concepts like nuclear-powered cryobots melting their way down with heat drills or autonomous underwater drones designed to unfold like origami once submerged linger on whiteboards and in labs. The challenges are monstrous, but so are the stakes. Europa's ocean isn't just a scientific curiosity, it's a test. If life can spark here in this dark, alien sea, then the universe might be far more generous with its miracles than we ever dared to hope. And that's a revelation worth melting through ice for. The cosmic web is the universe's grandest infrastructure project, a sprawling network of dark matter and hot gas filaments stretching millions of light years, weaving galaxies together like beads on an invisible string. These colossal threads, some as wide as entire galaxy clusters, form the backbone of the cosmos, funneling matter into dense nodes where galaxies congregate. But for all their importance, these filaments are ghostly realms so diffuse that a single cubic meter might contain just a handful of atoms, thinner than the purest vacuum we've ever created on Earth. That's what makes them both fascinating and maddeningly unreachable. They're everywhere, shaping everything, yet impossible to grasp. Picture the largest structure you can imagine, a mountain range, a continent, even the Great Wall of China. Now scale it up until it dwarfs all of them combined, and you're still barely scratching the surface of a single cosmic filament. The slime wall, one of the web's most famous strands, spans over 1.4 billion light-years, linking thousands of galaxies in a gauzy ribbon of hydrogen and dark matter. But despite their staggering size, these filaments are so tenuous that their gravity is the only clue to their existence. Gas within them is so sparse it emits almost no light, and the dark matter weaving through it is, by definition, invisible. Mapping them is like trying to trace the outline of a shadow cast by fog. Why can't we just send a probe? The distances alone are absurd. Even if we could travel at the speed of light, which we can't, crossing a single filament would take tens of millions of years. And there's nothing to land on. These threads lack solid surfaces or even dense atmospheres. They're more like cosmic cobwebs, offering no foothold for exploration. A spacecraft passing through would register nothing but near-perfect emptiness, its instruments starved for data in a desert of scattered particles. The few atoms present would be too energetic to capture, superheated to millions of degrees by the gravitational energy of the web itself. Our best views come from computer simulations and indirect tricks of observation. By studying how light from distant quasars filters through the filament's gas, astronomers can piece together their structure, like deducing the shape of a glass sculpture by the shadows it casts. The Hubble Space Telescope has caught glimpses of ultraviolet glow from filaments warmed by nearby galaxies, while future missions like the James Webb Space Telescope aim to probe their chemistry for clues about how they funnel raw material into galactic nurseries. But these are glimpses, not close-ups. The cosmic web refuses to be studied directly, hiding its secrets in plain sight. Yet these filaments are more than just cosmic decoration. They're the universe's delivery system, channeling gas into galaxies to fuel star birth and dictating where cosmic structures flourish or fade. Some theories suggest they might also trap rogue planets or even dark matter particles in their gravitational currents, creating invisible rivers of matter flowing unseen through the void. Others speculate that the web's pattern could reveal the universe's true shape, whether it's finite, infinite, or something stranger. So while we'll never walk these threads or touch their elusive substance, their very existence reshapes our understanding of the cosmos. They remind us that the universe isn't just a collection of stars and galaxies, it's a living network, constantly evolving, with hidden highways we can map but never travel. And perhaps that's the lesson of the cosmic web. Some structures are so vast, so fundamental, that they defy exploration not because they're distant, but because they're woven into the fabric of reality itself. Wormholes are the universe's ultimate shortcut, hypothetical tunnels through the fabric of space-time that could, in theory, connect two distant points in an instant. Picture folding a piece of paper so two dots touch, then poking a hole through both layers. That's the tantalizing promise of a wormhole, bypassing the vast cosmic distance between stars or even galaxies by slipping through a hidden corridor. But before you start dreaming of interstellar road trips, there's a catch. These cosmic passageways aren't just rare or unstable. They might be impossible without ingredients so exotic they border on magic. The math allows for wormholes, but barely. Einstein's equations of general relativity don't outright forbid them, but they come with conditions that read like a physics wish list. First, you'd need something called exotic matter, a theoretical substance with negative energy density. Unlike normal matter, which gravity attracts, exotic matter would repel, propping open the wormhole's throat against the crushing force of its own gravity. Think of it like trying to hold open a water-filled rubber hose with your hands. Without constant outward pressure, the walls collapse instantly. The problem: exotic matter has never been observed in nature, and lab experiments have only produced microscopic traces under highly controlled conditions. Even if it exists, the amounts needed to stabilize a traversable wormhole would dwarf the mass energy of entire stars. Then there's the instability issue. Classic wormhole solutions like the Einstein-Rosen bridge snap shut faster than a mousetrap the moment anything tries to pass through. Crossing one would be like stepping onto a bridge made of soap bubbles. It might look solid until you put weight on it, then pop. You're stranded in the middle of a black hole singularity. Some theories suggest quantum effects or higher dimensional physics could stabilize them. But these ideas are so speculative they're barely more than equations on a whiteboard. The lack of empirical evidence doesn't help. Wormholes leave no observable footprint, no telltale lensing or radiation signature that telescopes could detect. Even if one existed, spotting it would be like finding a single needle in a galaxy-sized haystack, assuming the needle doesn't vanish the moment you look at it. That hasn't stopped scientists from searching. Some have proposed looking for wormholes by their gravitational influence on stars, while others suggest gamma-ray bursts or cosmic strings might hint at their presence. So far, every lead has turned up empty, yet wormholes captivate us for a reason. They're more than just sci-fi plot devices, they're stress tests for our understanding of physics. If they're possible, even in theory, they challenge everything we know about causality, quantum mechanics, and the nature of reality itself. Could they be time machines creating loops where cause and effect unravel? Might they link to other universes, as some multiverse theories suggest? These questions linger at the edge of science, teasing us with possibilities we can't yet rule out or confirm. For now, wormholes remain cosmic maybes, shadows cast by the math we use to describe the universe. They remind us that some frontiers aren't just unexplored, they're unexplorable, at least with the tools and knowledge we have today. And maybe that's the most fitting irony of all. The very shortcuts that could make the universe smaller are locked behind barriers we can't yet cross. From the crushing depths of black holes to the frozen wastes of rogue planets, these 25 enigmatic regions remind us just how much of the universe remains beyond our reach, not for lack of trying, but because the cosmos itself seems to guard its secrets with cosmic locks. Whether it's the violent tantrums of magnetars, the ghostly pull of dark matter halos, or the silent expanse of the Boötes void, each of these frontiers defies exploration in ways that both frustrate and fascinate. And yet, that very inaccessibility is what keeps scientists and all of us utterly captivated. There's something deeply human about staring into the unknown and refusing to look away, about sending probes into poisonous atmospheres or telescopes to the edges of the solar system, hoping to steal even a glimpse behind nature's curtain. Think about it, every time we've cracked open one cosmic mystery, another has taken its place. The event horizon gave way to the singularity, which led us to quantum foam. Europa's ice hides an ocean which begs questions about life. The great attractor pulls us toward questions we can't yet answer, and that's the beautiful paradox of science. The more we learn, the more we realize how much we don't know. These unreachable places aren't just dead ends, they're signposts pointing toward the next great leap in our understanding. But here's the best part, the conversation doesn't end here. Which of these regions sparks your imagination the most? Is it the rogue planets drifting like cosmic nomads, or the Planck epoch, where time itself flickered into existence? Maybe you're haunted by the thought of white holes, or you're convinced the zone of avoidance hides something monumental. Drop your thoughts in the comments. Let's geek out over the universe's greatest unsolved puzzles together. And if there's a cosmic mystery we didn't cover that keeps you up at night, shout it out. After all, the next great discovery might start with a question, a theory, or even a wild idea from someone just like you. So keep looking up, keep wondering, and remember, the universe's most tantalizing secrets aren't just locked away in distant galaxies or buried under ice. They're waiting for the next curious mind to ask, what if?